Now, we just finished with the definition of a countable set. There are actually two different types of countable sets, so we'll define those here. So let X be countable. Right, and remember that means it has the same cardinality as some subset of the natural numbers. So if X is finite, so it has finitely many elements, then unsurprisingly, we call it a finite set. On the other hand, X could have the same cardinality as the natural numbers. So if X has the same cardinality as N, we say it's countably infinite. So those are our two types of countable sets. Either it's finite or it's countably infinite. So here's a theorem. Certainly n is countably infinite. Just the identity function on n is a bijection from n to itself, so certainly n has the same cardinality as itself. But here's a theorem. The integers z is a countably infinite set. Okay. So how does one prove a statement like this? So here's what we need. We need to place all the elements, this is important, all the elements of the integers z into an ordered list. And if we can do that, that will give us a bijection. So this is important. We have to know that all the elements appear in our list. So this is how it's going to go. So the only thing to be mindful of is that the integers contain all the natural numbers, but also negative numbers. Here's my list. So the first number in the list will be 0. The second number will be -1. The third will be 1. The fourth will be -2. The fifth will be 2. The sixth will be -3. And so on. So, once we're able to place the elements of z into an ordered list like this, there's a bijection. So there's a bijection that maps each integer to the natural number that it's labeled by. Right, so here there's a bijection that would map 0 to 1, -1 to 2, 1 to 3, -2 to 4, and so on. So here's our list. It gives us this bijection. Moreover, if we took any integer, we could say exactly where it should show up on the list. So this is important, and it goes back to what I wrote before, is that we have to place all the elements of z into an ordered list. So it has to be that I can find the location of any integer I want. So here's an example. I'm going to ask you to make it a little more precise in an exercise and then on homework. So for example, if you'll notice, every negative here is located or is labeled by the natural number that's minus 2 times it, right? Minus 1 is the second number on the list. Minus 2 is the fourth number on the list. Minus 3 is the sixth number on the list, right? So for example, minus 328 is the minus 2 times minus 328, which is 656th number. Right, integer in the list. Every integer does appear here. You know, if I gave you something like 5,491, there's some pattern that you can follow to tell me exactly where that integer appears in our list. So z is indeed countably infinite. Okay, there's maybe some details that I'd like you to fill in. So that's really what's coming next. Okay, so when we talk about bijections, we're normally talking about functions. I want you to actually define a function for me. So here's your first exercise. Right, give a function that describes the bijection, right, or represents the bijection, is maybe the better thing to say. So in our proof. So what we want is something of this form. We want to define f from the integers to the naturals by f of a equals, and then we have to go from here. So it's fine to do it in pieces. So it should be a piecewise function here, right? So it's sort of it's blank, right? Blank if a is whatever, blank if a is something else. Maybe you need more than 2 parts here. I'm not saying it has to be exactly 2 parts, but certainly maybe you want at least 2 parts in this function. And then on homework coming up, prove that whatever function we have is a bijection. Oh, sorry. So prove we have a bijection. Okay, so the integers are countably infinite because we can place them in bijection with the naturals. Here's a second exercise to think about. Requires less work, I think, than showing the integers are countably infinite. Just find a proper subset of n that's countably infinite. Right? Certainly n itself is countably infinite, but find a proper subset of n that's countably infinite. Right? And can you show it's countably infinite as well?